So far, we've done oligopoly models with homogeneous goods, right? So we had Cournot, where they chose quantity, and Bertrand, where they chose price, but the goods were the same no matter what model we were doing. So that's obviously not completely realistic in many markets, right? Some markets that might be more realistic than others. But what we want to do here is we want to add some sort of differentiation, right? What the book calls multicharacteristic differentiation. And it's really just the same thing that we did in chapter 7, introducing this parameter D into our demand curves. And so really we have two inverse demand curves that look very similar. We've gotten rid of the B just so we can concentrate on the differentiation term. And so firm 1's inverse demand curve is P1 equals A minus Q1 minus DQ2. And firm 2's inverse demand curve is P2 equals A minus Q2 minus DQ1. And this parameter D is just an index of product differentiation. So if we put D equals 1, then they're completely homogeneous. Consumers don't care between good 1 and good 2. When they're equal to 0, when D equals equal to 0, then that term just drops out of the demand curve and each firm is a monopolist. So between 0 and 1 is how much product differentiation there is, right? So it increases as we move from 1 to 0. So we can set this up the same way that we set up our regular Cournot. We just have a slightly different inverse demand curve. And remember, we have to add our fixed costs in order to get a sort of normal solution rather than a corner solution. And so firm I's profit is just, the inverse demand, that's P, A minus QI minus DQJ times QI minus CQI minus FI. And then we just distribute the QI through. We get AQI minus AQI squared minus DQIQJ minus CQI minus F. And then we take the first order conditions, very similar to what we had before. It's just we have this D term now. Set them equal to 0, and now again we have two equations with two unknowns. We can solve for Q1 and Q2, and it's actually not that difficult. And so if we solve for our equilibrium quantity, price, and profit, what we get is that quantity is A minus C over 2 plus D, excuse me. Price is A plus C CD over 2 plus D. And then profit is A minus C squared over 2 plus D squared minus F. And so remember that as D goes towards 1, they become, homogeneous products, right? So when D equals 1, we get our standard Cournot equilibrium, keeping in mind that we dropped the term B from our model just for simplicity. And when D equals 0, we get our standard monopoly equilibrium. So that's nice. So quantity and profits are falling as D goes toward 1, right? And so firms really want their products to be differentiated in consumers' minds. And so when they are completely, differentiated, right? So when D equals 0, then they have a monopoly. Here's the monopoly price on the vertical axis. And then as D increases from 0 to 1, right? D is on our horizontal axis here. We eventually get to our homogeneous Cournot price of A plus 2C over 3. This shows that, product differentiation leads to less price competition, right? That's the principle of product differentiation. And that is key to understanding a lot of what firms do, whether it's, changing the design of their product, changing the features of their product, changing how they brand their product. A lot of that has to do with differentiation so that they can move away from price competition. Now, Bertrand with multi-characteristic differentiation is a little bit more complicated just because of the algebra. So if you look in the book, you'll see they sort of redefine some new terms, beta and delta. I'm not going to worry about that too much. We'll see the solutions with our normal terms in the next slide. What we really want to focus on is the best response or best reply functions. Here, the best response functions have a positive slope, meaning that when you increase your price, I increase my price, and vice versa. And so we get an equilibrium here, P1 star and P2 star, But we can actually increase profits even more if we could collude, right? And if we can collude and agree to set prices even higher, then we'll earn even higher profits. And that's perhaps not that surprising. In Cournot, when you produce more, I earn less. But in Bertrand, when you set your price higher, I earn more. And so prices and output behave differently in the oligopoly. And so if we look at the Bertrand equilibrium with our original parameters, A, C, and D, we can see price is A plus C minus AD over 2 minus D. Quantity is A minus C over 2 plus D squared. And profit is A minus C squared times 1 minus D over 2 minus D squared times 1 plus D. So when products are homogeneous, right, when D equals 1, the model says, okay, Bertrand price equals C, and that piece disappears, right, because we get A minus A over there, and then 2 minus 1 in the denominator, so it's just C over 1. And when D equals 0, it again gives us the monopoly outcome, which is nice because it's nice to get to that when the model is saying it is a monopoly. And so equilibrium prices and profits increase as products become more differentiated, right? As D becomes to 0. And so in that way, once we introduce differentiation into the oligopoly model, the Bertrand model and the Cournot model actually start to look a little bit more similar. And it shows that differentiation is another way for firms to avoid that price cutting that is part of the Bertrand equilibrium and avoid that Bertrand paradox.